So in this video, I'm going to start a new topic of recurrence relations. So this video is just an introduction to that, looking at what we already know and just taking that very slightly further. So I would have a jotter and a pencil handy here. I'm going to ask you to do a task in the middle of the video and pause it, and there is no exercise at the end for today. So I just want you to have a think about what we do in this video. So firstly, a wee bit of revision on sequences. You will have looked at sequences in probably first or second year. So I suppose a wee bit of revision on what we did there. So a reminder that a sequence is an ordered set of numbers. For example, we might have 1, 2, 3, 4, 5, 6. And the way ellipsis here, you'll use that in English as well a lot. So the ellipsis means that that sequence goes on forever. It goes on to infinity, following the same pattern as it has done already. So if I just put this sequence into some sort of table here, so I've got my position in the sequence, that would be the first term is 1, the second term is 2, the third term is 3, fourth term is 4, fifth term is 5, sixth term is 6, and then I could find any term. So if I wanted the nth term, that would be n. So for example, if I wanted the 100th term, then the term would be 100. I could change it so that the position in the sequence, I was referring to it as n. So this is more common in maths as well. Now, if we look at a different example, for example, the sequence 1, -2, -5, -8, -11, -14, and so on and so forth. Now if we look at that in the table, with the position in the sequence being the first position, that number was 1. The second number was -2, the third was -5, etc. Now if I wanted the nth term, I would have to multiply the number of the term here by -3 and then add 4 to my answer. So just changing that so that the top row is referred to as n, and that just gives us a general picture of what's going on here. So that's what we've previously done for linear patterns. And if we wish to calculate the 100th term in a sequence here, we could do so quite easily using this formula, because it would actually save us having to list the first 99 terms. So if you look at, say, the fourth term here, if I just wanted to know the fourth term in that sequence, and I had this formula, then I would be able to get to -8. If I wanted the 100th term, like I said, that would be -3 multiplied by 100 plus 4, which is -296. I didn't need to know all of these terms in order to get the 100th term. So that's what we've learned before in linear patterns. So taking that just slightly further, and just keeping the same table here, the same sequence, it can be quite common for the position in the sequence to be referred to as un. So for this sequence here, we can say that u1 is equal to 1, u2 is equal to -2, u3 is -5, u4 is -8, u5 is -11, u6 is -14, and un is -3n plus 4. So the notation here of the un, that's slightly different. We've not met that before. So that is something that we're going to use moving forward in this topic. So that's worth bearing in mind. Now, here's a task for you. So look at the sequence below. What do you notice about it, if anything? Is there a rule? Is there something which was essential to find the next term in the sequence. So pause the video just now and basically have a look at the sequence and answer the questions. Okay, welcome back. So obviously if we were in the classroom just now, we would be having a bit of a discussion about what people noticed about this sequence. So hopefully you've noticed that to get a number in the sequence, to get a term in the sequence, you have to add together the previous two terms. So you can see that that third number there, which is 1, the third term, 1, is the sum of the previous two terms, 0 and 1. The same for 2, that's the sum of 1 and 1. Same for 3, it's the sum of 1 and 2. 5 is 2 plus 3. 8 is 3 plus 5. 13 is 5 plus 8, etc. Okay. Now, obviously the rule then is that you have to add the two previous terms together to get the next term. So what was essential there within this? Well, we needed to know the previous two terms in order to get the next term. Now, for those of you who are quite observant here, you might have noticed that this is the Fibonacci sequence, which is quite a famous sequence in maths. So you might have met that before. You may have talked about that lower down in the school in high school, or you might even have talked about that in primary school as well. Now, here's another sequence. I want you to do the same. Have a look at it. What do you notice? Is there a rule? And is there something which was essential to find the next term in the sequence? Okay, so hopefully you've noticed that, for example, the 5 here is 3 multiplied by the previous term, and then you have to add 2 to that. For the third term, 17, that's 3 multiplied by 5, adding 2 as well. For 53, 3 multiplied by 17, add 2. So it's all dependent on the previous term. So the previous term is absolutely essential to find the next term. So obviously the rule here is what I've said, it's 3 multiplied by the previous term and we add 2. Now, the reason I've got you to look at these tasks is it leads us on to recurrence relations. A recurrence relation is a type of recursive sequence which relies on knowing the previous term in order to obtain the next consecutive term. So obviously if we go back to this example, we needed to know the previous term in order to get the next one. And that is exactly what a recurrence relation needs as well. So it relies on knowing the previous term in order to obtain the next consecutive term. i.e., if we wanted to know the 100th term in a sequence, we would need to know the first 99 terms. So if you think back to what I did at the start of the video, for the nth term, we were able to just work out the 100th term in a sequence if we had a formula. But for recurrence relations, that's not the case. We need to know the first 99 terms. So, for the sequence 1, 5, 9, 13, we can see that u0 is equal to 1. Now u0, we've not referred to this yet, is the initial value in a sequence. Okay, so in any sequence has to have an initial value for an initial value defined for it to be a valid recurrence relation. So u0 is the initial term in the sequence, and here that is equal to 1. We then have u1 being equal to 5, u2 is 9, u3 is 13. Now, hopefully you can see some sort of rule here in this sequence. We're adding 4 to the previous term. So you can see in order to get 5, we're doing 1 plus 4, or u0 plus 4. In order to get 9, we're adding 4 onto 5, or u1 plus 4. Likewise for u3, that's the same as u2 plus 4. That's 9 plus 4 to give us the 13. So we can define a recurrence relation here. It's un plus 1, which basically just means the next term in the sequence is equal to the previous term in the sequence plus 4. Now, an example of a recurrence relation is gaining compound interest on money that you put into a bank account. Now, you've probably met quite a few problems, percentage problems like this in National 5. So I suppose the compound interest chat here isn't going to be alien to you as such. So you invest £100 in a bank account with an interest rate of 2%. So we know then that the initial value is U0, which is £100. So after 1 year, so U1, we are going to have in the account £102 because it's obviously an interest rate, so that's an increase of 2%. So that means that we've got 102% of the initial value. The 102% as a decimal is 1.02 multiplied by 100, which gives us our £102. So after 1 year in the bank account, we would have £102. U2, again, we are calculating an increase of 2%, but this time it's on the amount that was in the bank account at the end of the first year. So that's U1. So we're calculating that, and at the end of the second year, we're going to have £104 and 4 pence in the bank account. At the end of the third year, we're going to have £106 and 12 pence. And you can see that all of these calculations are dependent on the previous year, what was in the bank account the previous year. I.e., here, our recurrence relation, un plus 1, remember that was the next term in the sequence, is equal to 1.02 multiplied by un, which is the previous term in the sequence, where u0, that's the initial value, is equal to 100, and un is the amount in the bank account after n years. So this is the end of this video now, folks, and we'll come back tomorrow and we'll look a bit more at recurrence relations. Now, like I said, there's no exercise for today. I think all I want you to take away from today is this part here that we've got. This is how we refer to terms in a sequence, un. Okay, and when we're writing a recurrence relation, we use terms like un plus 1 and un. Okay, and remembering always that we have to have an initial value, u0, and if you can remember all of that, that would be great.